Welcome back to the deep dive. Thanks for joining us again. This is a continuation of part one of our EV charging system deep dive. In the first part, we covered, the purpose, the basic power block diagrams, conductive AC and DC charging, and the standard charger components. Today, we're plugging into a topic that's, well, quite literally electrifying our world: electric vehicle charging systems. Now, I know EVs are incredibly exciting, but let's be honest, the tech behind how they charge, it can sometimes feel like a bit of a complex puzzle. So our mission today is to cut through that complexity. We've gathered a stack of sources on EV charging standards, component breakdowns, you name it. And we're going to extract the essential nuggets for you. You're going to walk away understanding the different charging modes, the physical bits and pieces that make it all work, the vital safety measures, and even the challenges and, frankly, exciting future trends. The goal: for you to feel really well informed, ready for that next chat about automotive tech.
And that's exactly why this deep dive is so important. Understanding EV charging isn't just for the engineers anymore. It's key if you're thinking of owning an EV, or maybe investing in the sector, or really just grasping the infrastructure that's shaping tomorrow. What's fascinating is how just plugging in your car touches everything from grid stability to, well, how we design cities.
Absolutely. So let's kick things off by clarifying the fundamental charging modes. These are from the IEC 61851 standard, right?
That's the one, yeah. It basically defines how sophisticated and how safe the charging is.
Okay, so at one end you've got mode 1, super basic.
The most basic. Just plugging into a regular household socket, about 2.3 kilowatts AC power, and crucially, no real communication between the car and the plug.
Right. Then mode 2, I think I've seen those portable chargers.
Exactly. Mode 2 uses those, still AC, maybe 2.3 to 3.7 kilowatts, but there's that little control box on the cable. It adds a basic layer of safety and communication.
Okay, getting smarter. And mode 3, that's the common one for home chargers.
Mode 3 is your typical dedicated home wall box or public AC station. Much more power, up to 43 kilowatt AC. And this is where you get full two-way communication between the EVSE, that's the charging station, and the car. Really important for safety and smart features.
Got it. And finally, mode 4, the big one.
Mode 4. DC fast charging. We're talking serious power here, up to 350 kilowatts, sometimes even more. It has the most sophisticated control, all handled by the external charger, the EVSE. So these modes, they define speed, sure, but also intelligence and safety.
That makes perfect sense. Now, here's where it gets, well, maybe a bit confusing for people. The actual plugs, the EV charging connector types. It feels like a bit of a connector jungle out there, doesn't it? Depends where you are.
Oh, absolutely. It's very regional.
Like Type 1, I remember those on older Leafs, maybe some U.S. cars.
Yeah, Type 1, J1772, sometimes called. North America, Japan mainly. AC only, up to about 7.4 kilowatts.
Okay, and then Type 2 is the common one here in Europe, right? Yeah. India, too.
Type 2, or Menike's, that's the standard across Europe, India, Australia, places like that. Brands like Tata, Hyundai, Audi use it, handles more AC power, 22 up to 43 kilowatts.
Right. Now for the DC plugs, CHAdeMO.
CHAdeMO, big in Japan. Think Nissan Leaf, Mitsubishi. Still around elsewhere, but less common now. Delivers DC power, 50 up to maybe 400 kilowatts.
And the one that seems to be taking over, CCS.
The Combined Charging System, or CCS, it cleverly adds DC pins to the Type 1 or Type 2 connector shape. So you have CCS1 in North America, Ford, GM, VW use it. Up to 350 kilowatt, handles AC and DC.
And CCS2 elsewhere, Europe, India.
Exactly. CCS2 is the standard in Europe, India, Australia. BMW, MG, Mercedes, Audi. Handles even higher power, potentially up to 500 kilowatts AC and DC.
Wow. Okay, nearly there. China has its own.
China uses GBT. That's their standard. For brands like BYD, NIO, does both AC and DC up to about 237 kilowatters.
And finally, Tesla, the NACS.
Right, the North American charging standard. Used to be just Tesla, but now Ford, GM, and others in North America are adopting it. Pretty high power, up to 300 kilowatts AC/DC.
So this connector jungle, it's a real issue, isn't it, for drivers and for building the infrastructure?
It's significant. You might need adapters or struggle to find the right station, and for developers, it adds cost and complexity. Thankfully, we're seeing a global move towards CCS and NACS consolidating in North America. Things are slowly getting simpler.
Okay, let's peek under the hood then. What actually makes up the charging system itself? Starting with the EVSE, the charger unit.
Right, the box on the wall or the big station. Inside, you've got a few key parts.
Like the power section, what's in there?
Think of the power section as managing the electricity flow. It's got filters to clean up electrical noise from the grid, surge protectors for spikes, relays that only switch the power on when everything's safe, sensors to measure current, more filters for smooth output, and for the big DC fast chargers, a DC to DC converter to precisely control the power going to the battery.
Sounds robust. And the brains, the control part.
That's the control and monitoring unit. It's got a microcontroller, the MCU running all the logic, plus communication modems talking OCPP to the network backend or ISO 15118 for smart chat with the car. Sometimes Wi-Fi, LTE2, temperature sensors everywhere, managing inputs like buttons or RFID readers. It's making sure charging is safe, smart, and efficient.
And keeping cool is important, I imagine, especially for the fast chargers.
Absolutely. Cooling is critical. Simple AC wall boxes might just use natural air. Higher power AC or smaller DC might use fans forced air, but those really high power DC chargers, they need liquid cooling systems for the power electronics and sometimes the cables too.
Okay, then there's the cable and connector itself, the physical link.
The EV connector and cable system. Yeah, that cable is pretty specialized. AC cables have your standard power lines live, neutral, earth, plus 2 signal wires, CP and PP.
CP.
Control pilot and proximity pilot. They handle the communication handshake and tell the car the cable's rating. DC cables have the big DC positive and negative lines, plus those same CP-PP signals. And yeah, often liquid cooled for the really high power ones, 350 kilowatt plus.
And the plug and the car's inlet are designed to handle all those pins safely.
Precisely. Power, signal, ground, all securely connected.
Okay, shifting focus inside the car itself, what handles charging there?
So inside the electric vehicle, for AC charging, the key player is the onboard charger, the OBC. It takes the AC power from the wall or charger and converts it into DC that the battery can actually use.
But only for AC charging, you said?
Exactly. During DC fast charging, the OBC is completely bypassed. The external DC charger feeds power directly to the battery system.
Ah, okay. So the car's own control system manages that.
Yes, the EV controller and charging control logic. This involves the main vehicle control unit, VCU, coordinating things, and crucially, the battery management system, the BMS.
The BMS, that watches the battery health.
Constantly. It measures state of charge, SO theory, state of health, SO-H, temperature, voltage, everything to keep the battery safe and optimize charging. Communication with the DC charger uses specific protocols like CAN for CHAdeMO or power line communication over ISO 15118 for CCS.
It's a lot of complex tech working together. Which brings us to safety. This must all be underpinned by some serious safety and protection mechanisms, right?
Absolutely critical. There are multiple layers working silently in the background.
Like what? Give us an example.
Okay. Ground fault protection, GFP. Essential to prevent shocks or fires if current leaks somehow. This uses things like RCDs, residual current devices, or IMDs, insulation monitoring devices, constantly checking for tiny leaks or insulation problems.
Right. And protection against grid problems, surges.
Yep. Overvoltage and overcurrent protection. Uses SPDs, surge protection devices, circuit breakers, MCBs, fuses, plus smart software control that limits current if needed.
You mentioned temperature earlier, too.
Huge one. Temperature and thermal protection. Sensors monitor everything, power components, cables, the battery itself. If things get too hot, say 60, 70 degrees C, the charger will automatically reduce power. That's called derating.
And if it gets even hotter?
It'll shut down completely, usually around 80, 90 degrees C to prevent damage or, worst case, fire. This happens automatically, It's vital but hidden.
That's fascinating. So much is invisible to the user.
Exactly. There's also EMC protection against electrical noise, fire retardant materials, isolation barriers, sealed enclosures, connector interlocks so you can't unplug under load, and software constantly running diagnostics, ready to shut down if it detects a fault.
Puts your mind at ease knowing all that's going on. Okay, let's zoom out to the bigger picture. What are the key challenges in EV charging infrastructure right now?
Well, a major one is grid load and stability. As millions of EVs plug in, especially at peak times, it puts a real strain on the local power grid. You can get overloads, voltage drops. It's a big concern for utilities.
And the solutions.
Smart charging is key. Using communication like ISO 15118 and OCPP to manage when cars charge, spreading the load, and longer term things like vehicle to grid, V2G, where cars can actually feed power back to help stabilize the grid.
Interesting. Another challenge must be the cost?
Definitely. High cost of infrastructure deployment. Putting in chargers, especially DC fast chargers, isn't cheap. There's digging, wiring, communication links, often needing powerful transformers. An AC charger might be, say, $1,000 to several $1,000s installed, but a big DCFC. That can be tens or even hundreds of thousands.
Wow. So subsidies help there.
Subsidies, government programs, public-private partnerships, and designing more modular, scalable hardware are all part of tackling that cost.
And we already touched on the lack of standardization, the connector jungle.
Still a headache, yeah. Makes it harder for drivers, adds cost for multi-standard chargers. But like we said, the trend towards CCS and NACS is helping rationalize things.
What about using different charging networks? Payment issues.
That's interoperability between charging networks. Lots of closed networks mean you need multiple apps, multiple accounts. It's fragmented. The fix is open standards like OCPP and OCPI for roaming, and platforms like Hubject or GRB that let you use different networks seamlessly, like mobile phone roaming.
Okay, so challenges exist, but there's also a lot of exciting stuff happening. Let's talk future trends in EV charging.
Absolutely. The future's really dynamic here. Ultra-fast charging is a big one. We're seeing 800-volt systems and chargers pushing 150, 250, even 350 kilowatts or more. That means adding significant range, maybe 80% charge, in just 10 to 20 minutes for compatible cars. Needs serious power electronics and those liquid-cooled cables, though.
10 minutes. That's almost like filling up with petrol. What else?
Battery swapping. Instead of charging, you pull in. An automated system swaps your depleted battery for a full one in like 2 to 5 minutes.
So zero waiting time.
Pretty much. Great for high-usage vehicles like taxis and HIPs with grid load, but the big challenges are standardizing battery packs and the huge initial cost of setting up swap stations.
Makes sense. Any other cool tech on the horizon?
Definitely AI-based energy management, using artificial intelligence to predict grid load, optimize charging times based on electricity prices, even route drivers to the least busy charging stations. Very smart stuff.
And integrating renewables.
Yes. Solar-powered EV charging stations. Combining solar panels, often with battery storage on site, to power the chargers, reduces reliance on the grid, cuts the carbon footprint, makes charging potentially cheaper and possible in more remote locations. It's really interesting how these challenges are actually driving innovation, pushing us towards a smarter, more integrated EV ecosystem.
What an incredible journey to the world of EV charging. We've covered so much ground today, from the different modes and that connector jungle to the nitty-gritty inside the chargers in the cars, plus those vital safety systems working behind the scenes and looking at the big challenges and really exciting future trends. It makes you think, doesn't it? How this evolution isn't just about getting power into a car faster. It's really about a fundamental shift in how we interact with energy, with our vehicles, and maybe even our cities. Hopefully this deep dive gives you a fantastic foundation for understanding what's coming next. Do not forget to channel for more deep dive in automotive tech world in simplified way.